It's time for another amazing chemistry video with Mr. Stapleton, proudly sponsored by Farmer Junior Nice Coffee.
Welcome to part 2 of chromatography. In the last video I covered thin layer chromatography and the basic principles of chromatography, so make sure you watch that video first. What I'm going to do today is cover column chromatography firstly. We're going to focus on that, and then we're going to go into gas chromatography. Okay, so a quick reminder, alright, in chromatography we have a stationary phase and we have a mobile phase that travels over the top of it. Okay, so in column chromatography, basically we just flip it on its side. So we have a stationary phase, it's a column, okay? And what we normally do is we have a mobile phase that we then pass down through the column and we collect out at the other end, okay? Really good easy way to do this is using like a burette, for example, because you've just got that long column there. You can pour your solution in at the top, all right, which is your solvent, your mobile phase, travels down your column, and you can collect it out at the end, and you can control the rate of it with the tap in the burette. Okay, so what I'm going to show you is, again, I showed you in the thin layer chromatography one about black ink. I'm going to show you again, but this time just using a column chromatography principle. So if we start off with our column here, okay, so we've got our column. What we do is we've got our mixture at the top, which is our black ink dissolved in some form of solvent. Okay, now remember, generally what you want to do is you want to choose a solvent which is a different polarity to the stationary phase. Now the stationary phase here, we normally use what's called a slurry. Okay, and again we sometimes quite often use a slurry of aluminium oxide. That's just a really nice stationary phase which helps us to separate out components. That's on a very basic level, but you can obviously go a bit higher and get more in depth if you need to. But your stationary phase doesn't change throughout the course of it. So here in our column, alright, we've got our stationary phase, our mixture, our slurry through here. We pour the sample in and it loads up on the top of it. So that's just our solvent sitting at the top of on the top of our stationary phase. And what happens is, just due to the effect of gravity, that will start to move its way down the column. Okay. Now what you're going to see to begin with is something that looks a bit like this. Okay, so our sample, we poured on top, our black sample, it starts to move its way down the column. Now, some of the components, in this case the yellow component, is very strongly attracted to the mobile phase, or our solvent. So that travels very quickly through the column. It is very less strongly adsorbed to the stationary phase. So our yellow component comes out and we start to collect that down the bottom pretty quickly. You notice the red component stays here and the blue component is starting to only move very slowly, so it's very strongly attracted or adsorbed to the stationary phase. So what happens is they start to separate out. Once all this yellow comes through, okay, what we do is we go over to start collecting the red. But the really important thing is to know that you can actually control your solvent or your mobile phase that you're putting up the top of. You can change the polarity of that to help control the rate at which these separate. Okay, so what ideally you want to do in this sort of chromatography is actually get one colour here, a little white band of separation, a red colour here, a white band of separation, and blue. So you can add your solvent in, okay, to actually try and start separating those out. So once we've collected all the yellow, what happens is we move on to start collecting all the red. Okay, so the red starts to come through the bottom. You can still see the blues mostly up the top here. So now what we might do is change the solvent to encourage the red to move a little bit more fast. So we're changing the polarity of this to make it maybe, I don't know, slightly more non-polar, okay, or polar, depends on what the polarity is here, to actually make that move a bit faster. We don't want to make it move too fast, though. It will be too close to the blue component, because otherwise we'll start to mix them up again. So we just want to be able to collect all that red out, okay, and then ideally what we want to be left with is this bit here, alright, where we've just got the blue left at the end and we separate it out. Okay, so the phases we want to go through are these. Okay, so we want to start with our mixture poured on top, starts to work its way down by gravity, we separate out the colours and we collect each one individually. That's the process of column chromatography, and it still relies upon the fact that you have a stationary phase and a mobile phase, and you have a difference in polarity between them, and those components which are most strongly attracted to the stationary phase will come out first, Okay, those that are most strongly adsorbed to the stationary phase will stay closest to the top, okay, and they will move more slowly, and we can collect them at the end. So this is really, really useful just for separating different mixtures. Let's say you do a chemical reaction, you get maybe 6 or 8 different products, which is quite common, and you just want one of them. What you actually do is you'll run it through a column chromatograph, okay, and that will help to separate them out. You just collect the one you want. Did one at uni where I had about 12 different coloured bands, all right, and I just wanted 2 particular ones. So you just go through, you change your solvent to increase the rate at which different ones come through, and you can collect it at the end. Okay, really, really useful. Final one that I'm going to talk about is gas chromatography. Okay. Now, in the previous ones we looked at in thin layer chromatography and also column chromatography, we've used a solid stationary phase, and a mobile phase that we've used has mostly been a liquid. In gas chromatography, it's a little bit different because our stationary phase is still normally a solid, but it can be a liquid. All right. However, our mobile phase is actually a gas. Okay. This is really, really useful because sometimes your samples won't actually be liquids. All right, you may have gases you want to separate. Other times what you will do is actually dissolve your sample into a solvent, and then you'll vaporize it and turn it into gas particles and allow that to be separated. And there's a couple of benefits of that. Again, you only need really, really small amounts, okay? And it produces, rather than just having to collect it, it produces a digital readout, which I'll show you. Okay, so basically this is a very, very simple diagram of a gas chromatograph. Okay, so what you've got here is, in the middle of your gas chromatogram inside, you've got your stationary phase. So over on this side, you inject your solvent, okay, with your sample in it, which is your mobile phase. That gets vaporized. It passes through the column here. All the components start to separate out, okay, and then at the end over here, you've got a computer, okay. That's a computer, all right. That gives you a readout determining at what time it detected each of the components at the end of your gas chromatograph. Okay, so you don't need to worry about drawing that or necessarily knowing the ins and outs of it, but what you do need to be able to know is how to read a gas chromatograph diagram. So what you'll get is something that looks a little bit like this. Okay, so what we've got along here is the time on the x-axis. This is how long, or at different interval times, that we determine some readings on the computer. And this is the strength of the signal, and I'll come back to that in a minute. Okay, so what you've got to remember is that inside this gas chromatograph, so I'm just going to move that up a little bit, we've got a stationary phase, okay, and we've got our gas mobile phase moving across the top, okay, and that is a mixture of polar and non-polar components. Okay. Now, depending upon the polarity of the stationary phase, okay, let's say for this time we're going to go a polar stationary phase and we've got a non-polar mobile phase. Okay. So, as we know, all right, components that are similar in polarity to the stationary phase, so this case polar ones, are going to be really strongly attracted to the stationary phase. So they're going to move slowly. Whereas non-polar components are going to be strongly attracted to the mobile phase, and they're going to move quickly. Now, what you've got to realize is that the detector is detecting at what point these molecules, or what time these molecules actually exit the chromatograph. Okay? So in this case here, if we had a non-polar mobile phase and a polar stationary phase, non-polar components are going to come out first. Okay? Polar components are going to come out last. So on this diagram here, there's a couple of different things you can see. Okay, so the first thing you can see here, this little peak A, okay, right at the beginning, that's actually the solvent. All right, I'm going to try and match the colours up here. So the mobile phase, that's actually coming through there at the beginning. So the first thing we actually get out of here, these peaks here, those, in this instance, are actually going to be non-polar molecules. They are the first to come out, because they are most strongly attracted to the non-polar mobile phase, and they move quickly. The ones right down at the end here, okay, so this big peak, E and F here, okay, they are going to be the polar molecules. Okay, because these ones are these purple ones here that are more strongly adsorbed to the surface of the stationary phase, so they travel slowly. So they take longer to come out of your gas chromatogram. Okay, so that's really important to remember, because in this case here, all right, this time down the bottom, all right, the longer it takes to come out, all right, the more similar in polarity it was to the stationary phase. And you have to make sure you read the questions when they talk to you about and telling you what polarity is the mobile phase and the stationary phase. Now, the strength of the response here. The good thing about gas chromatography, unlike thin layer chromatography and column chromatography, is they only tell us what's in it and you can collect it out. This one also gives us an example of what percentage or ratio is in there. So what you've got to look at is the area under the peaks here. Okay, and that tells you the ratio of what your samples are. So it doesn't tell you how much they are, but just the strength of it. Okay, so you can see here that F, right, this polar component here, has a much bigger area under the peak than B or C. So that tells you there's a greater proportion of F than there is B and C in there. Okay, so the area under the graph can tell you how much of it there is in there as well, which is really important. So that's chromatography. We've been through thin layer chromatography, gas chromatography and column chromatography. They all rely upon that simple principle of a mobile phase and a stationary phase, and the difference in polarity of being either polar or non-polar. Okay, and then the molecules, the polar and non-polar molecules, being attracted to either the mobile phase or adsorbed to the surface of the stationary phase. If they're adsorbed to the surface of the stationary phase, they travel slowly. If they're attracted to the mobile phase, they travel more quickly. Okay, hope that helps. Practice reading your graphs, okay? Practice getting your head around it. Go back and look at the first video if you need to. And as always, ask me if there's any questions. Thanks, guys.